So we've all seen those spider web diagrams of social networks, right? But how do we actually make sense of them? Today, we're going to go beyond the basics. We're exploring the powerful, hidden math that allows computers to see, to understand, and even predict the behavior of these incredibly complex networks.
Okay, so here's the plan. We're going to tackle 4 key challenges. First, how do we even get a computer to understand what a network is? Second, how do we find the most important players inside it? Third, we'll look at how to uncover hidden communities. And finally, we'll see all this math in action solving real-world crimes. Let's get into it.
All right, our first problem is a big one. It's fundamental. How do you take something as abstract as, a network of relationships and translate it into a language a computer can actually process?
I mean, just imagine trying to map every single friendship on a huge social media site. You could create this massive chart, right? A matrix listing every person against every other person. Then you'd put a 1 if they're friends and a 0 if they're not. But just think about that for a second. How many of those possible connections actually exist?
The answer is not that many. The vast majority of entries in that giant chart would just be 0. You'd be wasting an insane amount of memory and processing power just to store information about connections that don't even exist. So the key here is we need a much smarter way to do this.
And that smarter way is called a sparse matrix. And the genius of this idea is really its simplicity. Instead of wasting all that time recording every single non-connection, a sparse matrix only lists the connections that actually exist. It's kind of like writing a guest list for a party. You only write down who's coming. You don't write down the billions of people who aren't. And to put that into perspective, look at this number. This represents the sparsity from a sample network in our research. It means that over 72% of the data was just empty space, total wasted potential. By using a sparse matrix, we can essentially just throw away all that useless 0 information and focus only on the connections that matter. That is a massive gain in efficiency.
All right, so now our computer can see the network efficiently. Great. Now we can start to build our understanding. So the next question is, what can we actually do with that data? How do we start asking interesting questions, like who is the most important or influential person in this entire network?
Well, it turns out importance in a network isn't just one thing. It can mean a lot of different things. Are you looking for the most popular person? Or maybe the best connected bridge between different groups? Or the person who could spread a rumor the fastest? To answer these different questions, we use a set of mathematical tools called centrality measures, and each one is designed to find a different kind of key player. Let's take a closer look at betweenness. Okay, think of a person who's the only link between 2 different departments at a company, or maybe 2 separate groups of friends. Any information has to flow through them. They are, quite literally, a bridge. Betweenness centrality mathematically finds these indispensable people by calculating all the shortest routes in the network and then seeing who sits on the most of them. Now, the whole idea behind closeness centrality is really intuitive. It just measures who can spread information the fastest. Imagine you want to start a rumor. Who in your network could get that rumor to absolutely everyone else in the fewest number of steps? Well, that person has the highest closeness centrality. They're the network's super spreader, basically a perfect gossip hub. And then we have what might be my personal favorite, eigencentrality. This one is the ultimate, it's not what you know, it's who you know metric. Seriously. You could have only 2 connections, but if those connections are to the 2 most influential people in the entire network, your eigencentrality score will be sky high. Your influence comes from the influence of your neighbors. This same idea is the foundation of Google's original PageRank algorithm. It works by imagining a random surfer just clicking links on the web. The pages that this surfer ends up on most often, those are considered the most important. So a link from a really important page acts as a much more powerful vote for your page's importance.
Okay, so we can find key individuals. But what about groups? Let's move on to a trickier problem. How do we find clusters or cliques or whole communities that aren't immediately obvious just by looking at a network map?
Take a look at this. It doesn't matter if we're tracking a disease outbreak or, like in this case, a money laundering network. You can see these distinct clusters of activity. The thing is, these groups weren't pre-labeled. They were discovered by the math itself. So, how do algorithms actually find these hidden structures?
The technique is called community detection, and the goal is to split the network up in a way that the connections inside a group are way denser than the connections between the groups. A really popular and effective method for this is the Louvain algorithm. It basically shuffles nodes between communities over and over, constantly trying to find the arrangement that gives the highest possible modularity score, which is just a measure of how good the community structure is.
And Louvain is just one way to do it. There are other incredibly powerful techniques like spectral clustering that get even deeper into the math. They analyze the fundamental mathematical properties of the entire network's matrix to find its natural fault lines. The perfect places to slice it into distinct, coherent communities. It's pretty cool stuff. So we've talked about these abstract mathematical concepts, sparse matrices, centrality scores, community detection. Now let's bring it back to the real world. Why does any of this actually matter?
I think this quote from a study on money laundering really says it all. This isn't just some academic exercise. Finding the key players in the hidden groups allows law enforcement to be strategic, to focus their limited resources right where they'll have the biggest disruptive effect on a criminal network.
And the results, well, they can be staggering. Take Operation Trojan Shield, a massive FBI-led sting. By analyzing the network data from an encrypted phone service they secretly controlled, they were able to get this: over 1,000 arrests, 40 tons of drugs, and more than $48 million seized. That is the real-world power of applying math to networks.
And it's not always about these massive stings either. This little story from an FBI bulletin shows the power on a much more human scale. Analysts found a key link, a previously unknown associate of a suspect. And just by talking to that one person, that one mathematically identified node, they created enough social pressure to make the suspect turn himself in. That's a direct, life-saving outcome driven by network science.
So we've seen just how powerful this all is. The mathematics of networks lets us see hidden structures, identify critical players, and uncover secret communities. It gives us a brand new lens to understand everything from friendships to criminal enterprises. So the question we're left with is, what should we point this powerful lens at next?